Hello guys, welcome back to my channel. Today we're going to be looking at the Morph's theorem combined with trig identities. So we're going to be using the Morph's theorem to construct some trig identities. And we're going to get right into it. Now, in my previous videos, we did outline the concept behind the Morph theorem, so you can watch the previous videos and you'll see the concept taking place. Now, according to the Morph theorem, let us say let z equal to cos theta plus I sine theta. We know that if we, for instance, were to take z and square it, so z squared, this would be equal to cos theta plus I sine theta all squared. Now, according to the Morph's theorem, z squared would be equal to cos 2 theta plus I sine 2 theta. Alright, let me just highlight this right here and keep it right here. But we could also find z by taking the binomial expansion. So cos theta plus I sine theta squared, which makes it a perfect square. And let me just quickly remind you how we expand the perfect square. Say if we have a plus b all squared, when we expand this, we will end up with a squared plus 2ab plus b squared. Alright, so expanding this bracket, what we do is use a comparison where a would be cos theta and I sine theta would be b, and then we simply populate the right hand side. So we can say that cos theta plus I sine theta all squared equal, and according to this it says I should square a, and a is cos theta. So you know when we square cos theta, we get cos theta all squared, but we can also write it as cos theta or cos squared theta, but let me do this for now. Cos theta squared plus 2ab, so it's going to be 2 times cos theta times I sine theta. So it's going to be, let me put the I there, I 2 cos theta sine theta. And also, this is actually a pretty interesting identity here. And then we square this last term, so we have b squared, so plus I sine theta all squared. Alright, let me just expand this out. This is going to be cos squared theta and plus I 2 cos theta sine theta. Or it doesn't matter, I could say 2 sine theta cos theta. So let me write it as 2 sine theta cos theta, if that's what most of us know the identity as. Now, I squared is negative 1. So this will give me a minus sine squared theta. But notice, when we apply the Morph theorem, we would have applied it to cos theta plus I sine theta squared, which means that these two things must be equal. Let me have it here, because this is also z squared. Alright, so we can equate the two identities here, because z squared is equal to z squared, the law of equality. So we could say that this implies that cos 2 theta plus I sine 2 theta is equal to cos square theta plus I 2 sine theta cos theta minus sine square theta. Now, what does the law say? The law of equality of complex numbers says that if two complex numbers are equal, the real parts are equal and the imaginary parts are equal. What does that tell me? Let me change the color here. So this would imply that cos 2 theta would be equal to the real part on the right, which is cos squared theta minus sine squared theta. It also implies that the imaginary part, which is sine 2 theta, would be equal to the imaginary part, which is 2 sine theta cos theta. And this is how powerful the Morph theorem is, because if we really look at these two identities, we definitely would recognize them from our knowledge of trigonometry. And we have just used the Morph theorem along with the binomial expansion of the brackets to construct these very two powerful identities, right? That is the Morph theorem along with binomial expansion. This is powerful. So when you get the next question, they might ask you to prove that cos 5 theta equal. So we know that the cos part is the real part and the sine part is the imaginary part. And we're going to be looking at one of those kind of questions pretty soon. Now, before we go any further, we're going to be looking a bit at Pascal triangle and binomial expansion. So let's go ahead and get the triangle for us. So we have 1, 1, 1. And the properties are, you can see a whole heap of properties in terms of the Pascal triangle. So it starts with 1. To get the middle term, we add the two terms at the top. So we add 1 and 1. We have 2. And it ends with 1. And the pattern is replicated. So we have 1. We add 1 plus 2. That is 3. We add 2 plus 1. That's 3. And then it ends with 1. And this keeps going. So you have 1. You have 1 plus 3. That is 4. 3 plus 3, that's 6. 3 plus 1, that's 4. And then it ends with 1. So we use a Pascal triangle to get the coefficients when carrying out a binomial expansion. What do I mean by that? When we have a plus b all squared, we know we expand in a bracket to the second power. So we're going to be interested in this line of the Pascal triangle right here. Now, the first thing that will happen is that the a will take the power of the bracket. So you're going to have a squared. The a counts down and the b comes in. So you have a, b. The a goes down to 0 and the b comes in. So you have b squared, right? And we add them. What is missing now is the coefficients. And if you look at this line here, you realize that the coefficients are 1, 2, 1. So the coefficient of a squared would be 1, the coefficient of ab would be 2, and the coefficient of b squared would be 1. Let us move on to a plus b all cubed. The concept is pretty similar, and as you can see here, it follows a pattern. The a takes the power of the bracket and b takes the power of 0, so I'm going to have a cubed. The a counts down, so it goes to a squared. The b comes in. The a goes down again, so you have a. The b goes up, so you have b squared. And then finally, the a goes away, or the a goes to a power 0, and you end up with a b cubed. To get the coefficients, we go back to the Pascal triangle, and we'll look for when we have 3. So it's going to be 1, 3, 3, 1. We don't need to input the 1, because once we say a cubed, we know the coefficient of a cubed is 1. What about a bracket raised to the 4th power? Of course, we use the next line. And of course, the first line is when the bracket is raised to 0. The second line is when the bracket is raised to a power 1. The third line is when the bracket is raised to a power 2. And the fourth line is when the bracket is raised to a power 3. So let us think about it when a bracket is raised to the power 2. So if I have, not 2, 4, a plus b to the 4th power. This is going to be equivalent to, same pattern, a to the 4 plus a counts down, so you have a cubed b. A counts down, b counts up, so you have a squared, b squared. And then I'm going to have a, b cubed. And then I'm going to have b raised to the 4th power, which is the power of the bracket. And that's when we stop. So the coefficients are 1, 4, 6, 4, 1. So I'm going to have 4 here, 6 here, 4 there, and then 1. So you can clearly see the pattern. I'm going to put back this in. So I'm going to have, this is b, and this is 4 a b cubed plus b to the 4. And you can take the Pascal triangle further. So it is with this Pascal triangle now that I'm going to apply the Morph's theorem. So I have to know how to expand this, so it becomes easier for me. Alright, here's an example of a question. Use the Morph's theorem to prove that cos 5 theta equals 16 cos to the 5th theta minus 20 cos cubed theta plus 5 cos theta. Alright, so we're going to start by applying the Morph's theorem. But knowing that cos 5 theta is actually the real part of the complex number, the Morph's theorem doesn't just apply to one part, it applies to everything. So by the Morph's theorem, I'm going to consider cos theta plus I sine theta raised to the 5th power. I know it's to the 5th power because this is saying cos 5 theta. By the Morph's theorem, this would be equal to cos 5 theta plus I sine 5 theta. That's the first part. Now, to construct the identity, I'm also going to have to expand it by using the Pascal triangle. So, by Pascal triangle. And I would have shown you how to construct the Pascal triangle. Now, what I want is the coefficients for when a bracket is raised to the fifth power. So what I'm going to do, I'm going to go back, because I had stopped my Pascal triangle at 4. So I'm going to go back and just write the Pascal triangle for the fourth power, and then just input how we'll actually get the coefficients for the fifth power. Now remember, the Pascal triangle starts with 1. So you have 1, then 1, 1. I'm going to skip out a few spaces, right? And go down to the fourth power where I had stopped in the previous question. So I have 1, 4, 6, 4, 1. Which means that for the bracket to the fifth power, it's going to be 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then it ends with 1. So those are the coefficients I really need to expand this bracket using the Pascal triangle. So by Pascal triangle, we're going to have cos theta plus I sine theta to the fifth power. Alright, and we know the pattern. First term in the bracket would be raised to the power of the bracket. So I'm going to have cos theta to the fifth power. Now, of course, I sine theta will be raised to the 0 power, but I don't need to put that in. And the first coefficient is 1. The second term, the cos theta counts down, so we have cos theta to the fourth power, and they're going to have I sine theta to the first power. And you know, once the power is 1, we don't need to put that there as well. Then to get my next term, it's going to count down to cos theta to the third power, and the I sine theta goes to the second power. Now notice for my third term, my coefficient is actually going to be 10. So I'm going to have 10 here. Alright. For my fourth term, the coefficient is 10. So I could even start off with 10. I'm going to have cos theta to the second power. And I'm going to have I sine theta to the third power. Alright. And then the next coefficient is 5. So I'm going to have plus 5. In bracket, I'm going to have cos theta. And in the next bracket, the I sine theta moves from cube to the 4. So I'm going to have I sine theta raised to the fourth power. And finally, the cos theta is going to go away. And the last coefficient is 1. So I'm going to have I sine theta to the fifth power. Now, what I'm interested in is only the real part. Only the real part in this. Good? So I'm going to have to equate the real parts. I'm only interested in the real parts. Now what I could start by doing is to equate the cos 5 theta plus I sine 5 theta to all of this. Because I don't necessarily have enough space here, what I'm going to do is go directly to the real part. Bear in mind you're interested in cos 5 theta, which is the real part. So you're also interested in the real part down here. So I'm going to say by comparison and see what happens. Cos 5 theta, which is the real part, when we apply the moivre theorem, would be equal to the real part down here. How do I know the real part? Now, I know that I squared is equal to negative 1, which means that if I have I cubed, it's going to be equal to negative I. And if I have I to the 4, it is going to be equal to I. So, all the parts that have I sine theta raised to an even power would automatically be real. Because once the I is raised to an even power, it's automatically going to cancel out. It's either going to be negative 1 or positive 1. So in the first scenario, cos theta to the fifth power would definitely be real. There's no I there. So I'm going to have cos theta to the fifth as my first real term. Now it means that the next term would be imaginary. Because notice you're going to have I to the power 1. So the other term, the term after that, would be the real term. So you realize that there's an alternation. So the first term, that's real, imaginary, real again, then imaginary, then real. Now, look at how we can analyze this. If you look at inside of this bracket, you're going to have I. And we know that I raised to the second power, I squared is equal to negative 1. So it's going to make this entire term negative. So what I'm going to have is negative 10 cos cube theta sine squared theta. it means that the next term that we have here is actually imaginary, which means that the term afterwards would be real. Now, what about I to the 4? I to the 4, we can look at it as in terms of I squared times I squared. And I squared is negative 1. So negative 1 squared is positive 1. So I'm going to end up with a positive 5 cos theta sine to the 4 theta. Alright, do we have any other real parts? No, because if this part is real, it means automatically the next part is imaginary. Now let us try to see if we can tidy things up here. If you look at your answer is in terms of cos theta only. So we need to get rid of all the signs in this expression here. Let's go ahead and see if we can get it to hold in one line. I'm just going to reduce the size on the left here. So we reduce the font to get some more space. Alright, so you can see everything that is on the right now. Now, as I was saying, my answer is in terms of cos theta only. So I need to get rid of all the sine theta. And this is where your trig identities come in very handy now. So we can say, recall that sine squared theta is actually equal to 1 minus cos squared theta. So the question might be, what about sine to the 4 theta? Now, sine to the 4 theta can really be written as sine squared theta squared. Alright, very important to know that. This is by laws of indices. So in this case, I could write this as sine squared theta squared, sine to the 4 theta. So that I can also populate. So this is going to become cos to the 5th theta minus 10 cos cubed theta. In bracket, you're going to have 1 minus cos squared theta plus 5 cos theta. And instead of writing sine to the 4 theta, we're going to have it as sine squared theta squared, which means that we can replace this sine squared theta with 1 minus cos squared, and we'll put by the squared. So I'm going to have 1 minus cos squared theta, and all of that is squared. Taking it down now, we can now expand our brackets. So I'm going to have cos to the 5th theta minus, if I expand this bracket, I'm going to have minus 10 cos cubed theta. Negative times negative is positive, so we have positive 10 cos cubed theta times cos squared theta would be cos to the 5th theta. Alright, plus 5 cos theta. Now this bracket is a perfect square. So when we apply the perfect square to it, I'm going to have 1 minus 2 cos squared theta. And of course, we have to square the second term, which is going to give me cos to the 4 theta. Good. We're almost there. So this becomes cos to the 5th theta minus 10 cos cubed theta plus 10 cos to the 5th theta. And of course, I'm going to expand this entire bracket now. So I have 5 cos theta times 1, which would give me back 5 cos theta. 5 cos theta times negative 2 cos squared theta would give me minus 10 cos cubed theta. And then 5 cos theta times cos to the 4 theta would give me a positive 5 cos to the 5th theta. Now all we have to do is look for like terms. So how many cos to the 5th theta do we have? We have 1 here, we have 10 here, and we have 5 there. That is going to be 16 cos to the 5th theta. What about cos cubed theta? You have minus 10 cos cubed theta, and you have minus 10 cos cubed theta. That is minus 20 cos cubed theta. And then looking for the last term, which is just cos theta, you have positive 5 cos theta. So therefore, cos 5 theta is equal to 16 cos to the 5th theta minus 20 cos cubed theta plus 5 cos theta. And that is exactly what we wanted. So we can say QED, that which has been proven. Very interesting proof actually.